Okay, calculus, I'm not sure what happened, but I had a lot of technical difficulties, so I'm just going to have to pick up where I think the first video left off. And I was describing the ln of x as the integral from 1 to x of the reciprocal function 1 over t dt. Then I described that the definition of e was the integral from 1 to e of 1 over t dt. Well, I was starting to describe this, and it said, and I think I might have covered it, but just in case it didn't come through, when I make this an e, that means this whole value is equal to ln of e. But I know ln of e, it's 1. So this is telling me that the integral from 1 to e of 1 over t, so that's this value, 1, whenever I get, when I get to the spot where this integral, I'm going to move away from 1, and when I get to the spot where this area, this integral, is equal to 1, then I am at e, which is very interesting. And that's how, when you first introduce e, a lot of textbooks, including ours, wait till we've had integrals. So you can define e like this. So I actually used e and taught you the derivative and everything before actually telling you about e in this way. So it's very interesting. All right, I'm going to then go ahead and take that information that I started with today, and we said the integral of 1 over u du is going to be ln of the absolute value of u plus c. So we're going to work with that, and we're going to do some examples to get you ready for your assignment. All right, the first one isn't too surprising. We're going to do this one. So I'm going to pull the 2 across the integral sign. And now I just have a version of this. So it ends up to be 2 ln absolute value of x plus c. The only thing is, because of ln, we can use log rules. So that 2 can run down and back and become a squared. And once I square this, I don't even need the absolute value anymore, because it's always going to be positive when I square it. So you may find that your book jumps to an answer like this, and you may wonder why yours didn't originally look like that. So they probably had that kind of thinking going. So I'm sure you can follow that. What about the integral of 1 over 4x minus 1, 1 over 4x minus 1 dx. All right, so at this point, we have an expression under here. So I'm going to try to see if I can do a u substitution along with these things. So what if this is u is, because when I look at the formula, I want a u on the bottom and a du on the top. So if this is u, what would du be? So in my u substitution thinking, 4x minus 1, I want that expression in the denominator to be u, hopefully, and du dx is 4, and du is 4 dx. So I need a 4 to complete substituting this whole thing from x to u. So I'm going to put a 4 in here and adjust for it out here. So you've seen that kind of action before, and now we're just doing it with a new integral, this one. So now I do have, I'll put in my u's now, 1 over 4 dx is du, and 4x minus 1 is u. So I do have du over u, so I can jump right to the ln of the absolute value of u plus c, but I don't want to end with u's, I want to end with x's. So I go back. U is 4x minus 1. All right. Let's do a couple more. Let's find the area. Let's use this. I'll give you the picture of this. So I'm going to find the area between the x-axis, x equals 3, and this graph. The graph will look something like this. I know it kind of comes up from the origin as sort of a mountain that kind of goes something like that. And we're interested, I said, between the x-axis, x equals 3, and the curve. So that will be this. So that will be the integral of that curve from 0 to 3. So let's give this one a try and see if we can get the integral. Then we'll plug in the upper limit of integration and the lower, and we'll be good to go. So, all right, I see that this, whenever I notice that this is or almost is the derivative of this, then I'm suspecting a u, an ln of u type of thing. So I'm going to go in that direction with my u box. So I'm going to say u equals x squared plus 1. And then I'm going to say du dx equals 2x, and du equals 2x dx. So we're almost there. I need a 2 there, so I can always remember the only thing you can put in and adjust for are constants. Can't do that with variables. So we have the integral of, we have 1/2 the integral from 0 to 3 of du over u. So we're good. So that's going to be 1/2 times the ln, absolute value of u, evaluated between 0 and 3. So I'm going to put in 1/2 ln of 3 minus ln of wait a minute. Oh yeah. ln of u, let me see. Alright, before I put in the 3, I can't put the 3 into the u. Sorry about that. Can't put that in yet. I have to go back to x, because these values, 3 and 0, are, when we started, we had a problem all in x. So I'm going to go back to the x value, which was x squared. The x value was x squared plus 1. Right there, and we are going to go from 0 to 3 now. Alright, so 1/2 ln x squared plus 3 is 10 minus ln of 0 squared plus 1, ln of 1. So I'm going to get 1/2 ln of 10, and ln of 1 is what exponent do I give e to get 1, so it's just 0. So I end up with 1/2 ln of 10, and I plug that in. This is the exact answer, but it's around 1.151. Alright, so when you're doing these kind, I just want you to always look for situations. I'm not going to do this one, but just discuss it. Like, I want you to always look now for an expression like a u here and an almost or an exact du here. So look at the expression on the bottom and notice it would be 3x squared plus 1 to be the derivative. So whenever you have an expression behind an integral with the derivative above an expression, so you have the expression on the bottom, its derivative on the top, you're going to end up with this ln situation. So always be out, on the lookout for that. And there are some situations where they are disguised, but I'm not sure I have time to go over that tonight. I think I will, though, so this will be part 3. So you might have the day off, and so you can enjoy the whole show. All right, be back in a sec.